Again, does anybody have any questions before we start? All right, we talked about temporal moments, earlier in the morning, using the physical non-equilibrium model as a motivating example. In this one, we want to talk about spatial moments. And remember, spatial moments, when we introduced them, especially in 1D, we were going from minus to plus infinity, so the domain is changed. What we want to do is essentially say what we would do if we wanted to do spatial moments, let's say for the same P and E model. What kind of differences would we be seeing? Also, I thought it would be a good idea for us to look at how moments look like or what happens to them in higher dimensions. So right now when we're talking about moments, we think of essentially a curve as a function of time, or one single curve as a function of space, and we think of that as a probability distribution function. So there's a higher order extension to it in 2 and 3 dimensions, and I can loosely say it extends very easily into higher dimensions, but it's not always very easy. But in principle, the same definition, but you have to just think about them in higher orders. So what I'll do is just show those to you and give you an idea of what they looks like. Their interpretation is similar, but now you have to think about, instead of moments about a centroid and so on, you have moments about axis or moments about a plane, and we use those to analyze 3-dimensional plume behavior. Okay. So spatial moments. I should perhaps see your notes too. So spatial moments, again, you'll have to excuse my notation, I'm not very consistent. I'm again, at least in this slide, I'm again using m sub n, but now to indicate spatial moments going from minus to plus infinity, c of xt dx, at least it is still in 1 dimension. And when I say recall Fourier transforms, there is a f missing over here. The Fourier transform of this function, is that so in your notes also, or is there an f there? If not, you should put an f. So it should be something like f of c of x comma t. So for Laplace transform, we are using c hat. For Fourier transforms, let's say we use c, and I'm using omega ft. Okay, and then this has minus to plus infinity as minus j omega x, okay, dx. So the Fourier transform of this, so there should be f over here and then f over here. And earlier when we were talking about Fourier transforms, so this would be one definition of a forward Fourier transform. So 1 over 2 pi and whatever would have to be absorbed in the inverse Fourier transform. But as I said, throughout this course, it's never our intention to take the inverse transform of anything, because we just want to stop with moments. So if this is the definition for the Fourier transform of c of xt, Fourier transform of the nth moment would be Fourier transform of this entire quantity, and you would essentially have this. If you were to expand this in infinite series, do term by term integration, you would get an expression like this: j is square root of minus 1. Okay. In this construct, you would essentially get this expression, and therefore you know what the nth moment is in terms of the Fourier transform. Okay. What we can then show is, if I basically normalize these moments with the 0th moment, x of t, we will call that as m1 over m0. So this basically says how far the plume has essentially moved. Effective velocity has this expression. So x of t is showing you where the centroid is of the plume as a function of time. How fast that centroid is moving as a function of time is our definition of effective velocity. Similarly, we can find the variance, or the normalized variance, and we said our effective dispersion is going to be half of the time derivative of how fast this variance changes. Okay, so this is what we talked about. Okay. Wow. Okay. So three-dimensional solute transport behavior. This is all condensed notation for us. This is essentially how bulk concentration the bulk concentration changes in a control volume with respect to time. This is essentially the gradient of the fluxes in the x, y, and z direction in vectorial notation. Okay, so x, y, and z direction, and so that is equal to minus gamma times C sub B. Gamma is the decay rate that is occurring for all the solute that is existing in the bulk volume. Then this bulk volume, therefore C sub B is now a function of x, y, z, and t, all of them. Okay, and our boundary condition is, so this is at t equals 0, that means at time 0, all of it is released a mass of solute m. Again, there should be no comma over here. All of this is released at the origin. So all the mass is just released at the origin, and then with time it will spread and it will move wherever, but now it's going to be like a huge cloud that is spreading and moving around in the flow field. Okay. Our definition of flux, let's say in the x direction, has this definition, same as we had before. We would have similar definitions for fluxes in the y and z directions. That would form this. That would form the three components of this overall solute flux. So now, how do we define spatial moments in high dimensions? So far we were either looking at time or at space. So now we are looking at space, but in space we have three dimensions: x, y, and d, x, y, and z. So our definition for a spatial moment, let's say we have the bulk concentration. It's a function of x, y, z, and t. It's a spatial moment. So basically I raise x to a certain power, y to some other power, z to some other power, multiply it with c and integrate in the spatial dimensions. Okay, and I define that as my spatial moment, but its order is j, k, n, because I have three dimensions. Okay. And in this case, just as a matter of definition, m prime, this was bulk concentration, this is the liquid resident concentration. In fact, the difference between those two would simply be equal to the porosity if nothing else is happening. Right? If all it's doing is essentially, if all the solute is only in the mobile solution, then that's how they are related. But this is our spatial definition of spatial moments in higher dimensions. So instead of just having one curve, we are thinking of an entire cloud, which is three-dimensional in space. Okay. And my 0th moment would then try to basically see how much mass of solute is there in this entire cloud now. Okay. So three dimensions, obviously. So this is our extension. In one dimension we had simply x to the power of n. Three dimensions, we have x, y, and z, each of these raised to a different power. And like I said, we have a moment, its order is going to be dependent on what j, k, and n are. We could, in principle, do a three-dimensional Fourier transform. Here in the last slide, again, x is the only spatial dimension that we have. In principle, we can have x, y, z, and t and do a three-dimensional Fourier transform. So the Fourier transform, instead of being a function in one dimension, it's a three-dimensional function. And we can, in principle, again define moments, or these moments, these moments j, k, and n in terms of derivatives of this three-dimensional moment transform and take the transform parameters to 0. So that is one method. The other method that we had briefly talked about when we were doing a one-dimensional problem was take the governing differential equation. In that case, we multiplied all the terms, since it was one-dimensional, by x to the power of n, and then integrated all of them from minus to plus infinity. So we can do the same thing here. We have a governing differential equation. We multiply each of these terms by x to the power of j, y to the power of k, z to the power of n, and then integrate each of these terms from minus to plus infinity in all the three dimensions. Okay, we could do that. In shorthand notation, this is what it would look like. Okay, so we would have x, y, z, each of them to the nth. This is the entire differential equation. D omega simply says dx, dy, dz, and that should be equal to 0. Notice the decay term has come in over here. Looks complicated. So what happens is, the first term that we have is a derivative with respect to time. Okay. So if this is C sub B, our definition of the moment will because the definition of the spatial moment, this is a temporal derivative, so this will simply become the nth derivative with respect to time. Just as we did for the one-dimensional case, when we had the one-dimensional case, we essentially had, we have the advection term that undergoes one spatial derivative. The dispersion term undergoes two spatial derivatives. So they get multiplied by whatever power, nth power or n minus 1th power, depending on the first or second derivative. Same thing happens. So this is essentially in mathematical notation. So what we are having is this first term, mjkn, derivative with respect to t. We have a gamma over here. This is supposed to be C sub b. No, that's wrong in my notes also. So this is gamma times C, the subscript is only on B. Okay. So that term, if I do this, since this is gamma is a constant, I'll simply get gamma times the jk nth moment. In the x direction, the spatial derivative with respect to x will simply give me the first power over here, j, q of x, and then m prime, m prime, because now we are in the resident concentrations, this will become j minus 1. For the dispersion term, I'll have j minus 1 because of the two derivatives. The dispersion term, I'll have the porosity, and now I have m prime because it's a resident concentration, but the moment order is j minus 2 in the x direction. Similarly, for the y direction, I'll have k with the advection term, k times k minus 1. This moment will be of a lesser order in k by 1, over here lesser order in k by 2, and essentially the same thing in the z direction. So this is what I mean by saying that the extension is same, but now you have to carry much longer equations along with you. Okay. But whatever we did with one dimension, we are simply now doing it in 3 dimensions. And notice that here I have, because these are bulk concentrations, I have m, because in the flux terms we had resident concentrations, we have m prime, but in this particular case m prime and m are simply related by the parameter porosity. Okay. So they're all equivalent. Our initial and boundary conditions essentially say that the moment mjkn at time t equals 0, so this quantity is going to total mass that is released only when j and k and n, all of them are 0. So initially, if all the solute is released, it's existing over there only for the first moment, the 0th moment. The first, second, third moment, since that is where it's released instantaneously, all of those are 0. But as time goes, then those will evolve. So what we essentially end up then is with a differential equation where the unknown is the moment, just like we had in the previous time. So we have moment generating functions. So those functions are going to be generating moments. Moment generating differential equations are differential equations, the solutions of which will yield the moments directly. We are not solving for the concentration, we are directly solving for the moments. And just as in the previous case, the way these are structured, essentially the jk nth moment requires us to know the j minus 1, the j minus 2, or the k minus 1, k minus 2, n minus 1 and n minus 2 moments already. That means I have to first solve for lower order moments. Once I have the lower order moments, they go on the right hand side, and then I solve for the next higher order moments and so on. So that is our strategy. And that then is moment generating differential equations. So in 3 dimensions, the algebra becomes a little more messy, but we can still at least define moments the way we have done before. So we can do some simple things. Let's first start by setting j equals k equals n equals 0. Okay. So in this particular equation, if I put j, k, n equals 0, all of these are 0, I'll have these as 0. Notice that all these lower order ones, j minus 1, j minus 2, k minus 1, k minus 2, which I haven't computed, they're all essentially going to be zeros. Okay. Because I'll have terms like n and n minus 1 multiplying them. If n is 0, that term is already gone. So the first moment, what this tells me is what is the total mass in my 3-dimensional plume. That is because by definition this is simply the concentration integrated over the entire plume. So what I get a simple differential equation with an initial condition of m. Its solution is simply m times e to the power of minus gamma t. So all it says, the total mass that's there in the plume with time it's going to decay by this particular rate. Okay. If I set j equals 1, k and n equals 0, that means I'm looking at the first moment in the x direction. So it's like, because this plume now is moving in 3D, the first moment in the x direction is how far it has moved, the centroid of this plume has moved in the x direction. Okay. And if I go ahead and set up that equation, I'll get an equation like this. I'll solve for it and I get an expression for m100 comma t, which essentially says how far the plume is going to be moving as a function of time. Okay. If I set j equals 2, k and n equals 0, I'll get another equation which I can solve. I get the second moment. In the other directions I'm not doing anything. I've left them as 0 for now. I'll get an expression like this. So what this is saying is I have this three-dimensional plume. If I set k and n equals 0, my first moment says this plume has moved in the x direction. How far has the centroid moved along the x direction? I could have done the same thing in the y direction and the z directions. I would have got the coordinates of the centroid in the y and z directions if I went through that. Okay. What is this saying? This is essentially our interpretation of the second moment, how much the plume has spread in the x direction. Okay. It's just now you are thinking of a three-dimensional cloud now. If I go back and define my effective properties, just as we have done before, so v times d by dt of m100 m00, I get v sub x. If I get d effective in the x direction, I simply recover dxx. So what this means in this model, in this particular model, apart from advection and dispersion, the only thing happening is decay. So when I calculate the effective property, the effective velocity in the x direction is simply the advective fluid velocity in the x direction. The effective dispersion in the x direction is simply the dispersion coefficient in our differential equation in the x direction. Nothing else is modifying them. So the gamma term, effectively it's not either slowing the plume down, it's not changing dispersion, because it's acting on all of them and the entire plume in the same way. It's just that it's reducing everywhere in the same way. It's not affecting how fast it moves, it does not affect how it spreads, just that the values, the concentration are going down. Okay. So that is what we would expect. So in principle we could do the same thing in the other dimensions, and we would get effective velocities in the y direction to simply be equal to v sub y, the advective velocity in the y direction, and similarly d effective of y and so on. So in this case, obviously the effective properties, you are simply going to recover back the original velocity and dispersion that you had in each direction in the original equation. Okay. Any questions? So we are not going to show higher order moments. We typically only do up to first or second to talk about effective velocity and dispersion. And we will talk about another model, a simpler model perhaps for 3D, but let's come back to our example earlier in the morning when we had the non-dimensional physical in the non-equilibrium model in non-dimensional terms. We had all these equations. The only change I have made is instead of omega, I have put alpha bar over here for the parameter for the Damkohler number, which governs the reaction rates. The reason is it's very common in the Fourier transform to have omega as your transform variable. So we didn't want to have another omega, which would really confuse the situation. Okay. So this alpha bar is essentially now the Damkohler number. Okay. We would have these definitions. Now notice that I have two Fourier transforms that I want to take. One is for C1 and one is for C2. And what we will do is define using m sub k to define the Fourier transforms or the moments which are coming from C1, and n sub k to get the moments for C sub 2. So we have two different concentrations, if you will, okay, that we have to worry about, mobile and an immobile concentration. So we can go ahead and do that. Otherwise, and now it's an infinite domain, minus to plus infinity. So our boundary condition says that at time t equals 0, it's a one-dimensional problem. So at time t equals 0, all the mass of solute is introduced at z equals 0. And with time, then it's going to spread in both the positive and negative directions. And as I indicated, when you have this happening, so there is some solute mass that escapes into the negative z direction as the plume spreads and it moves, but after a while all of it will then come back and go back into the positive z direction, because advection will pull it along in that direction, and eventually it will not be spreading far enough to go into the negative direction, right? So it's something that we are aware of. So if I then go ahead and do that, if I use the Fourier transforms, I take the Fourier transform of both the equations. Wherever we have the spatial derivatives, notice that we will carry an omega square and an omega that we get along with them. The time derivatives are essentially remaining the same. Because the concentrations are 0 at minus and plus infinity, all the boundary terms essentially tend to drop out. Our initial conditions are that since all the mass was added in as concentration in phase 1 liquid phase, at time t equals 0, that whole mass is here. For C2, initially it's 0. So we end up with a system of equations for the two unknowns, C1 tilde and C2 tilde. And then we have to solve the system of equations. And so those are going to be typically difficult to solve, because by and large you'll have a system of equations that you have to worry about. Unlike Laplace transforms, where you have one ordinary differential equation, when you do spatial moments, you are essentially integrating out the space dimension. So you are left with this kind of a system where A11, A12, A21, and A22, these are the coefficients which you get from this equation, but they are going to depend on omega, Peclet number, beta, retardation coefficient, so on. So you'd have to solve for this as a function of time to get C1 hat and C2 hat. So this would be the Fourier transforms. Once you solve the Fourier transforms, then you'll be taking their derivatives with respect to omega, setting them to 0 to get the moments. It's become a little more complicated now. Okay. So typically it is difficult to solve, except for, another typo, it's supposed to be except, not expect. Okay. Okay. So we are going to leave it at that and say, that does take a lot more work. I want to simply come back to the 3D equation, but I want to talk about mobile immobile region model, because that is a simpler model. Okay. So mobile immobile region model, we essentially get this particular differential equation. We have concentrations in the mobile region. Concentration in the immobile region is connected to the concentration in the mobile region through this difference. Otherwise, all the flux that is happening only in the mobile region. Okay. And the initial condition says all the mass rests in the mobile region at x, y, z when they are all at the origin. Immobile region has no concentration. This is our definition for the moment, same as what we had previously, but in terms of the mobile region. So again, we could do the same thing that we did, find expressions for m, j, k, n of different orders, and even for the mobile immobile region, which is simpler than the physical non-Euclidean model, you're going to get long expressions, and so that is why we don't, or at least I am very reluctant to carry out all that algebra. So in this case, m00 is going to have this kind of form, the 0th moment. m1 divided by the 0th moment only in the x direction is going to look like this. m2, that means only in the x direction, divided by the 0th moment will look like this. And you can do the same thing in the other dimensions too. Other dimensions, it's going to be a little simpler. And the term that A that you see over here, you are going to get some, so it's basically long algebra. That's why we don't spend too much time. However, if after we do all this, I can still define my effective velocity as this and d effective as this, but notice that d by dt of all of this, m100 by m00 was this whole term, and it has t in various places, so you have to take its derivatives. D effective would essentially be given by this kind of an expression. So extension to higher order dimensions, it can be done, but the thing is that algebra becomes a lot more tedious. They're carrying a lot more terms. You have to interpret it in 3 dimensions. It becomes a little more complicated, but the basic principle is still the same. Okay? So I just wanted to show you what complications arise in 3 dimensions, and we are really done early today. Any questions? So the major message over here is we can do spatial moments. If we have things like the PNE model or the CNE model, we have a system of two equations. Unfortunately, when we are done with the transforms, we end up with a system of equations. Okay. System of equations are more difficult to solve. We are getting a system of equations for the transforms. If you do solve for the transforms, you have to later on come back, take the derivative of the transform with respect to omega and set them to 0 to get the moment. So that does become quite tedious, and it's not analytically available very easily. For the mobile immobile model, you can do it, but it is like, even for that, you can see that the algebra is fairly tedious. Okay. So in 3 dimensions, again, we're not spending a whole lot of time, and there are things that you can do in 3 dimensions, but the extension of the definition of the moments is somewhat similar. Instead of x raised to being 1 power, we have x, y, and z each raised to different powers, and then we define our moments. Any questions? All right, I think perhaps tomorrow we will look at some very clever ways of doing these, some of these moments, or cleverer ways of doing this. I also promise that you are able to ask me any questions that you wanted, since we have an exam later today. So I'm going to be here till noon at least. If needed, I can be here longer too. Any questions? All right, we'll stop over here to give them a chance to